were looking at the demodulation of angle modulated signals. We had discussed several ways of doing this, and we were now trying to develop a mathematical model for the balanced discriminators that we talked about earlier, right. If you remember, a balanced discriminator is essentially two slope detectors which are used together to form an overall discriminator such that the output is proportional to the input frequency deviation, right. That is the purpose of a balanced discriminator. The second purpose of the balanced discriminator is, and that is the reason why it is called a balanced discriminator, is that the output of this balanced discriminator should be equal to 0 when the input signal has a frequency equal to the carrier frequency, right. So that the 0 or DC input response of the FM signal is maintained. Okay. So if you recollect, we were first looking at this idealized model of the slope detector, which is not that of a balanced discriminator, but that of an unbalanced discriminator, right. The idealization was, we assumed that we had a slope detector, slope circuit whose frequency response was proportional to the frequency deviation from FC, but it was going only on one side. But well, it was going on both sides, but it was having a DC response equal to a non-zero DC response corresponding to FC, right. So the FC is somewhere here, and as your input frequency varied around FC, the response of the circuit would vary linearly in this fashion, right. That is the slope detector. This, of course, this circuit is followed up by an envelope detector whose output is proportional to the modulus of this, and therefore the output is proportional to the frequency deviation of the input signal as we want, but with the difficulty that at the carrier frequency the response is not 0 but some finite value, right. We analyze the circuit mathematically by using a complex envelope representation of this filter, this circuit, which is like this, and we went through these equations describing the input and output, and finally reached, if you recollect, this equation for the output complex envelope in terms of the input, which was taken to be this. This is the complex envelope of the input, this is the complex envelope of the output, and as you can see, this is S tilde t here, the complex envelope of the input. As you can see, the modulus of this, which represents the envelope of the output waveform, right, is given by pi bt, basically this term, the multiplying term, right, because the modulus of this will be unity always. So this is the output, that expression for the output in terms of the input signal, and as you can see, this equation shows that the output envelope of this circuit, right, is dependent linearly on the input message signal MT as we want, with the problem that we have already discussed, that there is a DC component which we did not want, right. Basically it is the same thing that we physically argued earlier, that this slope circuit converts the FM signal or the angle modulated signal into an amplitude modulated signal, right. This represents the amplitude modulation, right, and this represents the carrier. The only thing is, in this case the carrier is not one of constant frequency, but the carrier itself is an FM modulated carrier. However, the way the envelope detector works, we have seen how envelope detector works, that is a diode followed by an RC circuit. It hardly matters whether the carrier has a constant frequency or whether the carrier phase keeps on varying, right. The operation of the detector is essentially based on detecting the peaks of the carrier, right. It tries to track the peaks, and it won't matter whether at times the cycles come close together or cycles are slightly far away from each other, right. Operation of the envelope detector will be such that it will produce an output which is proportional to the instantaneous envelope, which is precisely this, right. So, the modulus of this is equal to this, which is the envelope detector output. Now, what can we do to take care of the fact that there is a DC component present here, which we did not want, right? And as we know, the answer is to have a second slope circuit with somewhat different characteristics than the slope circuit that we are using here, so as to balance this out, right? That is what we need to do. So, what can we do to balance it out? So, let us look at that slope circuit again that we have considered. This was a slope circuit we took now at this stage. So, what should we do to balance this out? All we need to do is the following. We need to take a mirror image of this response, this frequency response around f equal to 0, right. So, if we consider an H2f tilde, which is like this, right, which is equal to H1 tilde minus f. Basically, I have taken a mirror image of this, right, around f equal to 0. If we do that, that is a slope, instead of being plus 4 pi a, is slope here is minus 4 pi a, and this is the exact relationship between the earlier circuit and this circuit, right. Then we will have a very interesting situation. Let us see what will happen. So, we will proceed with the analysis with this kind of a slope circuit in mind. So, we are considering a second slope circuit or slope filter, whose frequency response, complex frequency response of the corresponding low pass signal, low pass filter, right. You see, the actual filter is a band pass filter. This is a complex envelope representation of that. This is the low pass representation of that, more precisely, right. We are looking at a low pass representation, and the corresponding complex band pass representation would be something similar, except that it will be like this, right. Maybe if I can draw it, but let me first write down the equation for the low pass case. So, H2 tilde f, which is H1 tilde minus f, right, and if you remember the equation for H1 tilde f, what was it? H1 tilde f was j 4 pi a f plus bt by 2, right. That was the expression for H1 tilde f. So, what will be the expression for H2 tilde f? It is the same thing as this, except that f is replaced with minus f. So, this becomes j 4 pi a minus f plus bt by 2, right. And as you can see, this matches with what we have drawn here. At f equal to bt by 2, the output would be 0, the response is 0. At f equal to minus bt by 2, the response is the maximum value, which is this value, right. So, this is the slope circuit that second slope circuit that we are going to have. Now, if you compare this with some of the equations that we have looked at in this connection earlier, at which point will the things change, right. If you remember, basically what we have seen is, since H1 tilde f is like this, and I think, let me see which is the right equation. Yes, this is the one. This is the equation that we use to compute the output envelope in terms of the input envelope and the frequency response of the circuit, right. So, everything remains the same, except that H1 tilde f will get replaced with H2 tilde f, right. So, what will happen? Instead of j2 pi a f plus bt by 2, you will have j2 pi a minus f plus bt by 2, right. This f will get replaced with minus f, and if you go to the time domain, which was the next step was to go to the time domain. So the time domain equation here would become, instead of ds tilde by dt, you will have minus ds tilde by dt, because this is j2 pi a f s tilde f, right. The corresponding time domain operation is differentiation operation with a negative sign. However, this will remain with a positive sign, and everything else is same, right. So you will get the same expression as before, with a minor difference that the coefficient corresponding to this term will turn out to be negative. That is about the only difference. And which was that term? If you look at the final expression, out of these two terms, which is the one which is coming from the derivative? It is the second term. The first term is a constant term coming from here, right. So the first term remains as before, and the second term also remains as before, except that this plus sign gets replaced with a negative sign. So I do not have to repeat the analysis that we did earlier. We can directly write the result, right. And the result would be that S2 tilde t would be equal to pi times b sub t into a sub c into 1 minus 2 k sub f upon bt into mt. This is the envelope of the response. I am only writing the envelope, everything else is the same, right. So the second circuit, the second slope circuit, will produce an output like this. So what do I need to do to balance out the DC? All I have to do is subtract the two outputs. So if I look at S1 tilde t, envelope of that, minus the envelope of S2 tilde t, you will get an output which is equal to 4 pi kf a ac into mt. Bt will cancel off. Is that correct? And the overall FM balanced FM discriminator becomes, then we need to have a slope circuit with frequency response h1 tilde f or h1f. I think here I should not write h1 tilde f, simply h1f. That is a band pass filter, right. We need a second slope circuit h2f. We follow them up with envelope detectors, basically modulus operation, right, and subtract the two outputs, right. So that is the mathematical theory behind a balanced discriminator. So as you can see, the balanced discriminator that we discussed earlier essentially tries to realize this, right. Remember we had two tuned circuits, one which was approximating one slope circuit, the other which was approximating the other slope circuit. That is all that we had, and that was precisely what. So this mathematical theory now precisely explains why the difference in the envelopes of the two would be your required demodulated output. Okay. So I hope things now fall in place and you have a fairly good understanding of how those staggered tuned balanced FM discriminator work, right. This is the basic theory, and as I mentioned earlier, and I like to repeat it today, this is the most basic form of a discriminator. There are other improved versions of the balanced discriminator, about which I requested you to read yourself as a self study exercise. So, I hope that you will do that, okay, if you have not already done so. Okay. So, that is about FM discrimination or demodulation of angle modulated signals. Now, let me come back to a point which I mentioned sometime at the beginning of this discussion on FM discrimination or beginning of FM demodulation. You see, in all this theory also you would have realized that there is a different derivative involved, right, at various stages, right. There is a differentiation involved which we have used. Some form or the other differentiation comes into the picture, right, ds tilde by dt, and because of that your output envelope will have a in fact it not only because of the derivative but also because of this term. So, through both these terms you can see that if the input signal itself has envelope variations, right, they will be either passed on as such to the output, right, or worse still they will be accentuated, right, because of the derivative operation here, right. So, sometimes even though the envelope variations themselves may be small, the rate of variation, the derivative sometimes may be quite large, right, and they can get accentuated. So, your output in that case will be proportional not only to mt as it should turn out to be, because this entire theory was based on the assumption that the input signal had a constant amplitude, right. If the input signal does not have a constant amplitude and has an envelope of its own, time varying envelope of its own, not a constant envelope, then those variations will get passed on to the output, which we do not want, right. So, the balance discriminator that we have discussed so far is sensitive to amplitude variations of the input signal, right. So, that is something that you must appreciate. So, even the balance discriminator, whether it is balanced or unbalanced, it does not matter, the kind of discriminators that we have discussed are sensitive to, or this is sensitive to amplitude variations. Which we do not want, and we also discussed a remedy for this problem. What was the remedy? The band pass limiter, right. And basically I give you an intuitive feel for how does a band pass limiter work and what does it do. Let us develop a slightly better understanding of that to basically polish off our discussion on FM demodulation, because this is an important, a very essential, almost essential component of the FM demodulator. Before you pass the FM signal for demodulation into the FM demodulator or into the balance discriminator, you must pass it through a band pass limiter, right. The purpose is to recollect, to convert the input signal into a constant amplitude signal, right. The input signal which may have some envelope variations either because of some distortion introduced by the system or because of noise or whatever reason, right. We like to kill, if there are any amplitude variations present, we like to kill those amplitude variations. At the same time we like to get that FM signal back intact, and that is what a band pass limiter does for us, right. And if you remember, the block diagram of a band pass limiter is something like this. You have a hard limiter. Remember what is a hard limiter? Followed by a band pass filter. Tuned to the frequency Fc, the carrier frequency. This system as a whole is known as band pass limiter, right. So, the input to this is, we are saying, is a signal which not only contains your angle modulation, that is cosine omega c t plus theta t, but the instantaneous amplitude which should have been a constant value may have some temporal variation, may have some variation with respect to time, which we want to kill, because if you do not do that, the ds tilde by dt and s tilde t that are present in the relationship that we discussed will produce at the output some component which is not proportional only to mt, but also additional variations because of these things. And what we therefore hope the band pass limiter to do for us is to produce an output which is some a prime cosine omega c t plus theta t, right. We should keep our FM signal intact, but the amplitude variation should get killed. This is what we want, and this is precisely what this circuit does, what this system does. Let us see how, what is the theory behind this, how does it work to produce this, precisely this. It is fairly simple theory, but let us go through it, because it is important to have a very clear feel for these things. Let us start with the hard limiter. Hard limiter is a device, as I mentioned earlier, is something like a highly saturated amplifier, or you could say it is a clipping circuit which clips at 0, right. So, if you were to plot the output versus input characteristics, output voltage versus input voltage on an instantaneous basis, right, then for an amplifier it is a straight line passing through the origin, right. For a hard limiter it is a highly nonlinear system. This is what the characteristics are. If the input is even slightly positive, the output becomes 1. The input is even slightly negative, the output becomes minus 1. That is the definition of a hard limiter. As against hard limiting, we can have a soft limiter which goes something like that, right. It also limits ultimately, but it does not limit the moment the signal becomes either positive or negative, right. It carries out that operation more smoothly. So, in our case what we are saying is our input VIT is some AT into cosine of, let us call it phi of t, where phi of t is omega c t plus kf, let us say it is an FM signal, right. This is the input to the system. So, the output, so we can think of the output now as a function of phi. The input is a function of phi. So, think of for a moment the input not as a function of time, but as a function of this variable phi, where phi is this complete function of time, right. Phi of t depends on time. So, let us say there is a parametric relationship between phi of t and t, right. So, you can think of Vi as a function of phi, which is simply something AT cosine of phi, right. Let us try to understand this function a little bit. Now, let us particularly let us try to understand what is V naught as a function of phi. What can we say? What we are saying is this is going to be equal to 1 when Vi phi is equal to is greater than 0. Is that correct? V naught phi is going to be equal to 1 if Vi phi is greater than 0. And when will this be greater than 0? We are assuming, of course, A of t is always positive because it is the envelope, right. So, essentially whether Vi phi is positive or negative will depend on whether cos phi is positive or negative, right. So, So, it is equal to 1 if cos phi is greater than 0, and it is equal to minus 1 when cos of phi is less than 0. Now, if you forget the temporal relationship for a movement, forget about the time dependencies that we are talking about, right. So, what can we say as a function of phi? What is the nature of the function V naught phi as a function of phi? It is periodic, right, because cos of phi as a function of phi is periodic, right, and this has a dependence on the nature of cos of phi. Cos of phi is equal to is greater than 0 for half the time as 0 as phi goes from 0 to 2 pi, right, and it is equal to is less than 0 for the other half of the time. I should not use the word time, for half of the cycle and for the full cycle as phi goes from 0 to 2 pi, right. So, in as much as cos of phi is a periodic function of phi, V naught phi is also a periodic function in phi, right, and clearly therefore, and what kind of a periodicity is this? Suppose you were to plot this periodicity as a function of phi, it is a periodic square wave, right. So, V naught phi is a periodic square wave function of phi with period 2 pi. This is clear to everyone. If I plot V naught phi as a function of phi, it is essentially a square wave. Mind you, I am not plotting this as a function of time, I am plotting V naught as a function of phi. We are not caring how phi depends on time, that is a separate issue. As far as phi is concerned, it is a constant, we do not even have to worry about it. All we are saying is, as in fact we are not worrying about what is AT, we are worrying about what is V naught phi. V naught phi will not have any dependence on A of t, right, it will have a dependence only on cos phi. When cos phi is greater than 0, it is plus 1, A of t just disappears from the picture from our consideration, it is absolutely of no consequence. So, this is the important point, that this thing as a function of phi is a square wave function with a period of 2 pi, and therefore, I can represent this function in terms of a Fourier series, not as a function of time, as a function of the phase phi, okay. And I know what kind of a Fourier series a square wave function has, it contains only odd harmonics of the argument, right, and the precise representation is as follows. So, V naught phi, which is the square wave function, has this Fourier series representation 4 by pi into cosine of phi minus 1 by 3 cosine of 3 phi plus 1 by 5 cosine of 5 phi and so on. This is the Fourier series representation of V naught phi. So, now let us substitute for phi. We know what is phi. Phi is this function of time, right. So, we can write therefore that V naught as a function of what phi is, which is omega c t plus kf integral m alpha d alpha. So, this is substituting for phi, V naught as a function of this. So, I am bringing the time dependence back now, right, by substituting for phi, is equal to 4 by pi, and you will have all these terms, cosine of omega c t plus kf integral m alpha d alpha maybe I should not close this bracket here, minus 1 by 3 of cosine of 3 omega ct etc. and so on. Okay. You can think of this as a function of time now. So, V naught as a function of time, because this is now a function of time. So, I can, instead of saying this is a function of phi, I am writing it as a function of time, because the time dependence is very explicit in this relation. This is what we have. Okay. So, this is the nature of this is a series representation for the output signal at the output of the hard limiter. And what are we following it up with? We are following it up with a band pass filter tuned to FC, and as you can see, all other components of the Fourier series representation of V naught t, they are around 3 omega c, 5 omega c, and so on and so forth. So, if the bandwidth is sufficiently small to only cater for the bandwidth of the FM signal and reject the higher frequency components, you would simply remove all this, right? You will filter them out, and therefore your V naught t after band pass filtering let me call it V naught prime t, right, would be only the first term of this Fourier series, which is 4 by pi cosine of omega ct plus k sub f integral m alpha d alpha. So, as you can see, independent of what is the value of a of t, right, the output has a fixed amplitude equal to 4 by pi, right, and your FM signal, the FM variations remain intact as before, and that is how a band pass limiter works. So, I hope now with this discussion it is clear the role how a band pass limiter works, and it should also be clear that an overall FM demodulator must contain both these devices, right. It must first contain a band pass limiter, right, followed by preferably a balanced discriminator. And together they form your FM demodulator, right. In fact, many of the advantages of the FM signal that we will talk about later, particularly its increased tolerance to noise, comes from the fact that the demodulator is preceded by a band pass limiter, right. Without this, those disadvantages will not be those advantages will not be available to us. And of course, this is a required and necessary component for a proper FM demodulation, right, particularly in the presence of channel imperfections. If the channel is perfect, we do not need this, right. If the channel causes no amplitude distortion, no envelope variations of the input signal, we do not need a band pass limiter, but invariably channel will impose some distortions, will include some noise, and therefore there will be some amplitude variations, and therefore we need to have a band pass limiter, right. Any questions at this point? So, can we assume that the principles of FM discrimination and band pass limiter are sufficiently clear now? Okay. We are not through with FM demodulation as such, because what we have discussed so far is one class of FM demodulators which are basically open loop systems, right. They are systems in which we are trying to devise circuits such that the output is dependent on the input frequency deviation with respect to the center frequency, right. There are also closed loop FM demodulators, right, and which are also called feedback demodulators. So let us spend some time on those now. Because what we are going to discuss in this connection is going to be important from several points of view. These feedback demodulators, our initial motivation for their discussion is to show that they are very important classes of FM demodulators, right, or angle demodulators. However, they also have other applications, right. For example, applications to which we referred to earlier when we are discussing synchronous amplitude demodulation, right. We talked about the need for a local carrier which is synchronized with the incoming carrier, particularly when you wanted to demodulate DSP-SC signals, right. So how do you achieve that synchronization? That is again achieved through these same feedback devices which we are going to use for FM demodulation, right. So although our initial motivation is to show how these so called feedback demodulators can be used to carry out demodulation of FM signals, we will also discuss some other applications of these separately, right, or as we go along. Basically, the motivation for using these kinds of demodulators over the normal discriminators that we have discussed so far is that they yield improved performance, better performance in the presence of noise. It's improper to discuss it fully here because we haven't yet considered the effect of noise on FM and AM for that matter. But when we do that, let me just preempt that discussion a little bit. Let me give you a preview of that discussion. When we do that, we will find a very important characteristic. The important characteristic that we will study later is that while the FM in general is better in the presence of noise, it gives superior performance in the presence of noise, and that is why it is the preferred modulation to use for FM in FM broadcast in music broadcasting, right. It also has a disadvantage. The disadvantage other than the bandwidth disadvantage, which of course it has because it uses much larger bandwidth. The other disadvantage it has is it displays a phenomenon which is called threshold effect. The threshold effect refers to the fact that the output is very nice if the input is good, if the input signal to noise ratio is reasonably large, right. So there is noise present, but not to an extent that something bad happens, and this is the problem. In FM, if the input signal to noise ratio deteriorates beyond a certain point, becomes very bad, let us say, then the output of the FM demodulator simply fails to, it simply fails to resemble the input at all, right. The FM demodulator simply breaks down, right. So there is a certain threshold SNR which you must maintain at the input of an FM receiver, right. If your signal is not strong enough, then the output will be of very bad quality rather than of good quality, right. So this is the threshold effect which an FM receiver exhibits, the reasons for which we will discuss later, but it does that, right. So as you know, usually when the input SNR goes down, the output SNR also will go down. There is nothing wrong with that. That will always happen in any system, right. There is more noise at the input, there will be more noise at the output because typically you are working with a linear behavior, right. That will always happen. But usually this relationship will be a graceful relationship, right, so a proportional relationship. That is, if the input SNR goes by a certain amount, the output SNR also goes by the same amount, whatever the actual values. But if this relationship becomes worse than this graceful dependence, then that phenomenon we call the threshold effect, and that is what happens in FM, right. It is very nice up to a certain point, but it is very bad beyond that point. So it is either very good or very bad, nothing in between, something like that, right. As to why that happens, we will see that later. And one of the advantages of going for feedback demodulators is that it can extend the threshold, it can lower the threshold, for us, right. So that's one of the reasons. So it's widely used. So therefore feedback demodulators are widely used. And the second advantage of these feedback demodulators is that they can be realized, easily realized in integrated circuits form. So in the form of ICs. The reason for that is typically in these kinds of feedback demodulators we do not use any inductors, right. The balance discriminator that we discussed so far is based on the use of tuned circuits, staggered tuned circuits, right. The two slope circuits that we have talked about, they will be typically realized by using the linear portion of the FM tune of a resonant circuit, right, parallel LC circuit, right, whereas there will be no LC components in this realization, right. So that's the advantage of these feedback demodulators. Okay, there are two basic kinds of feedback demodulators, and we will discuss first the most important of these, the more important of these two. It's called the phase lock loop. Or PLL. So we are going to discuss the use of PLL for FM demodulation. But mind you, PLL is a very important component, and it has many applications. FM demodulation is just one of them. Now a PLL has 4 basic components. We'll discuss as to why we call it by this name a little later. Let me first describe what it is. It has 4 basic components, and there is a feedback involved amongst these components. The 4 components are: there is a phase detector, which operates on 2 inputs, right. Let us say there are 2 sinusoidal inputs here. The output of the phase detector would be proportional to the instantaneous phase difference between these 2 inputs. That is why we call it a phase detector, right. The output here would depend on the instantaneous phase difference between these 2 inputs. This is followed by a filter which is called a loop filter. Right. We may also have some amplification in the loop, so we call it a loop amplifier. Sometimes this is clubbed together with the filter, and so the filter itself has some gain, right. So it has some associated gain, and then you close the loop like this. In the feedback path, closing the loop, we have a VCO. Remember what is a VCO? A voltage controlled oscillator, which we have discussed in the context of FM signal generation, right. So a VCO is present in the feedback path of this circuit, and the input to the VCO at this point we will argue can serve as, if you feed an FM signal at the input, this input signal can be taken as the output, right. Let us call this output as E sub Vt, input to the VCO signal. We will see that under certain conditions E sub Vt will be proportional to the message signal Mt when the input signal happens to be an FM signal. Okay. Now how does it work? We will discuss in sufficient good detail as to how it works and what are its characteristics, but let me just give you a brief idea today. At the input you have an FM signal. Let us say input signal is X sub RT, which is A sub c cosine omega c t plus phi of t. It contains your FM modulation, right. It contains your message signal in terms of its dependence on in terms of the fact that phi of t will depend on m of t, right. It will be proportional to integral of mt, any FM signal. Your VCO here in this loop will produce some other signal of similar kind, right. We do not know what it will be exactly. So, let us say this VCO signal, let us call it E sub 0 t or E sub o t, that will be some A sub v sine of omega c t plus theta t, right. And the phase detector would try to produce an output as close to phase detector is sensitive to the instantaneous phase difference between these two, right. So, it will be sensitive to phi of t minus theta of t, and the feedback loop as any feedback loop will try to do is will try to drive this error to 0, right. This VCO is designed in such a this whole thing is designed in such a manner that it will try to drive this error to 0. So, if suppose that happens, we have to discuss whether that happens or not. Suppose that happens, basically what you are saying is this theta of t will try to follow phi of t, right. And if theta of t follows phi of t, what is the relationship between the message and the phase? The message is a derivative of the phase, isn't it? Message is d phi by dt. So, that means d theta by dt will follow the message, right. That means that the input to the VCO, because after all the instantaneous frequency of the VCO will depend on the input voltage, that means this input voltage will try to follow the message signal. That is the basic idea. So, if we can ensure that this loop is works in such a manner that the instantaneous phase of the VCO output tries to follow the instantaneous phase of the input signal, then the input to the VCO signal will try to follow the message signal, and therefore, you would have got at this point the message signal that you are looking for, right. Have you understood what I am trying to say? If not, tell me, I will repeat again. Any questions on this? No questions means what? You haven't followed, or you have followed? You are keeping absolute mum on this. Okay, we will stop here, think about it, and we will start at this point again next time.